Okay, guys, this is stats day 2, 7.1 day 2. If you guys have not watched the other video that's posted prior to this, please stop this video and go watch the one on statistic calculations. Very important. Also, if you've watched that, but you have not fully read this page that we're looking at right here, all the way to the bottom, you don't have to read all the charts, but go through and read the words in here, okay? And then read the second part of this whole thing. There's a lot of good stuff in there because I'm not going to go over it. I expect you guys to go over it. And here is, you should have seen in the video, the empirical rule is kind of nice and pictured right here. And bottom line, what this is doing is this is comparing, okay, this is actual. This is an actual composite score, not from WASA West, but somebody off of the ACT score report, and this is going through and showing you how you can read your ACT score and how we can kind of compare the statistics via your U.S. rank, your state rank, between your composite score, your individual scores in math, science, and all that good stuff. Okay, so all I'm doing is I'm coming through here. And what we're going to do is we're looking at this mean with the empirical rule, and most of this stuff should make sense if you have already watched the video on the stat calculations. Now, one thing we will be talking about today is we are going to be making the statistic calculations, okay? So what we're going to do is we're going to be looking at calculating how many standard deviations away are we from the mean. Remember, the mean, it's not mean, it's the mean of your normal curve. The mean and the median are the exact same thing. They are center peak of the curve, okay? And we're trying to calculate here with statistics to find percentages. We're trying to find out how many standard deviations away we are from the mean. And this is a very basic calculation of statistics. And what we do is we usually call that a z-score in statistics. And here is the formula how to find a z-score. Your z-score equals the value you are trying to find or use minus the mean of the distribution divided by the standard deviation of the distribution. Okay? And what we're going to be looking at here is, in a minute, maybe, let's erase that. If your z-score is a whole number, we can estimate it very easily by looking above the curve. So bottom line, we're saying, okay, so we know, I shouldn't have erased that, here's my mean, okay? Remember, the standard deviation is how far you are above or below the mean. In each color here, when I go from purple to green, the line dividing purple and green, hey, that's my cute little point of inflection right there. That's one standard deviation away. And looking at the curve, if the value is one standard deviation greater, oh, I didn't want to cross it out. The calibration is pretty bad. One standard deviation greater than the mean, hey, that means we're going to be putting here, and what percent of the population is below that red line? Well, it's going to be 34 plus 34 plus 13.5 plus 2.35. There will be 83.85% of the data values will be to the left of my standard deviation of a z-score equaling 1. My z-score is 1. 83.85% of all the data points lie to the left of the z-score, okay? It's really important to understand when we go to our z-table, the number we are going to be pulling out is talking about the area to the left of the z-score. It's never talking about it to the right. It's always going to be to the left of our z-score that we're talking about, okay? And then the one right underneath there, what if your value was 2 standard deviations below the mean? What percentage of the population falls below that? Well, whole new problem now, because now I got to look here. Okay, I'll put my mean back there again. I'll be nice and I'll put the mean back. Here's my mean or my mu. Okay, and if I'm 1, 2 standard deviations below that. Okay, this is z equals 2. My empirical rule allows me to easily calculate that. When I go to my z-chart, or my z-score reflects the area to the left of the curve, that would be falls below 2 standard deviations to the left, or below the mean, that would be 2.35%. A very small percentage is going to be the left of 2 standard deviations below the mean. Well, what are all these z-scores talking about? Well, z-scores, okay, what happens if my z-score is not a whole number? Well, 99.99%, it's not a whole number, okay? So what happens is, statisticians did a whole lot of work for you already, and they created this table that allows you to find the percent below any number of standard deviations. Now, if you look here, all these standard deviations on this first page that you're looking at, notice all these z-scores here, they're all negative. And because they're negative, that is talking about a z-score that is to the left of the mean. So to the left of the mean is a negative z-score. And when we crank on to the next page, these next ones here, let's get to the next page, because these z-scores are positive, they're talking about my normal curve right here. Here's my mean. These are standard deviations to the right of the mean. And all your z-scores have to be rounded to 2 decimal places. For instance, if I'm looking for a z-score that equals, I don't know, 1.42, okay? My left column here that I'm looking for, I don't want to erase, my left column, give me my highlighter, this column right here is giving me these first 2 decimal places. So what I need to do is I need to come down until I see 1.42, or 1.4 exactly. That puts me in this realm. And then if you notice the top, up here on the top, I'm going to try to make that a different highlighted color. Give me a different one. The top up here, what I got to do is I got to cross-reference the top. That is that last one because it's actually 0.02. And so then I take my 0.02 is going to go across the top. So I take my 1.4 and I got to come down to my 0.02 and I find the intersection of those. Okay, that means 99 if I'm 1.42 standard deviations away. That puts me somewhere right in here. That means to the left of that z-score, there is 0.92220, which will convert to a percent, 92.220% of all the data values are to the left of that z-score of 1.42. And that's how we will be using this, okay? And what we're going to do is I'm going to do the best I can, and I'm going to come here and I'm going to walk you through a couple examples, and hopefully you already know how to do these, maybe not, but bottom line, we have math SAT scores, okay? And let's say not ACT, these are going to be SAT scores, and what they're doing is they're telling me a couple critical pieces of information. The mean, or mu, or we might even call it X bar of the math scores are 500. That's my mean or my average. The standard deviation, which we call that little fella, is 100. And they're asking, ooh, this is kind of a technical one, what percent of SAT scores are above 62.5 or 625? So what that's doing, that's asking me, when I come here, well, that's 6, that's 700, so that's going to be right about here. They are asking me what percent are above 625. They want me to give them the area of to the right of that z-score. This is kind of putting a little different twist on it, but remember, underneath that curve is 100% of everything, okay? All of them in there. So that area underneath that curve is 1. Because if I convert my percent, my area is 1. Okay? So what we need to do is we need to find our z-score for this value. And my z-score is always going to be your x value minus mu. And I don't know if we're going to be using mu or x bar divided by, I think it's not, is that a lowercase sigma? I'm not sure. I'll find out. But sometimes we're going to call it mu or x bar. Okay? Difference is population mean, or population mean and sample mean. So we probably should be using, Mr. Wendling will get much more technical with this if you choose to take AP Statistics. So we're going to say minus x bar. Well, what is that? Well, that's my value I have of 625. I need to subtract my mean of 500 from that and divide it by the standard deviation of 100. Well, that gives me 625 minus 500, that gives me 125 divided by 100. And we always have to cram this into a decimal. That's going to be 1.25. That's my z-score. So my z-score, remember, this z-score is representing area to the left of my curve. So it's going to, when I go to my chart, it's going to be giving me this stuff when this is what I want. But I need to go back to my table. Because that z-score is positive, I must go to my positive part of my chart. So I got to go to 1.25. So I'm going to scroll down. I found my 1.2. Then I need to find my 0.5, and I need to come down and find the intersection of those two, which should be that 0.8435. So what this is telling me is this side of the curve over here is technically, I wrote this down now, 0.89435, which means if this side to the left of that is that much, if I need to know how much is above that, I know the whole area is 1. If I subtract my 0.89435 exact, sorry, that's going to give me 0.10565. And when I convert that into that density curve into a percent, it's going to be 10.565%. Only 10.565% of all SAT scores are greater than 625. Okay? And that's what we're going to do. So now I'm going to erase this curve. A lot of times I make a new curve, but it's going to be easier for me to use this one for you. And now in number 2, the second one here, they're asking me what percent of SAT scores were below 445. So what I want to do is I want to come here and I'm actually looking to say, hey, where is 445? Well, there's 400, there's 500 is my mean. Somewhere right here, notice that's below my mean. So if I want to know below that, this is the area I want to find, right? And when I get my z-score is going to give me that area, okay, underneath that curve. So what I'm going to do is I got to calculate my z-score now here, which my z-score, again, is going to be my data value minus the mean divided by the standard deviation, which is going to be 445 minus 500 divided by 100. And one kind of critical thing to know here, guys, is notice if this is my mean, notice I'm looking for a z-score less than the mean to the left of it. That means my z-score in the end better be negative. And why? Look at that. It's going to be because I get negative 0.5 or negative 55 over 100. And when I convert that into a decimal, that's negative 0.55, right? So now I need to take this z-score and I need to go to my z-table to find out what my percentage is. So I come back. Whoop, this is the positive side. I got to go back one more sheet. Now I got to look for, if I'm looking for negative 0.55, I am looking for the first two decimals, that's technically negative point or 0.55. So I'm looking for this down the left column, and which means here's my other one. I need to come across and I need to find my 0.5. So there I am. And then I need to come back up and I got to find my 0.05. So that's going to be this column coming down, and I'm going to track it. And I'm tracking this column down, this column across. Please don't do this in all your z-scores because you're going to blot it all out. So there is the intersection right there, 0.29116. That gives me my z-score of negative 0.55, or the area for the z-score of negative 0.55. So when I take this over here, I take 0.02, no, oh, I already forgot what it was. I got to go back and look now. So when I go back there, what was it? 29.116, 29.116, 29.116, 29.116, 29.116, 29.116. Then I need to take, because that's the area under the curve. Remember, the area equals 1. I need to convert that into a percentage, which just means shake and shimmy my decimal 2 places, 29.116%. Please don't chop it off, guys. You're getting 5 decimal spots out of this Z-chart. Do not chop them off. Do not round them. Use them all every time, okay? So now we're going to take a different approach here on the tree diameters. And on these tree diameters, we know the mean is 11, standard deviation is 3. So we're asking what percent, it's important, percent of diameters are below 10 inches. Well, my mean's right here, and I want to know below, this is going to be 10. So I'm looking for this area right here, right? And then I'm going to convert that into a percent. Well, how do I do that? Well, I find a z-score. My z-score is going to be my data value minus my mean divided by my standard deviation, which is 10 minus 11 divided by 3. Okay? Notice they're going to give us these right now. That's going to give me negative 1 over 3. Well, yeah, that equals negative 0.3333. We need to adequately every time, guys, round perfectly to 2 decimal places, which means when you're doing a z-score, you better be looking at that third one, and that one tells you whether that guy goes up or down, because, yeah, it does matter. It does matter. Our z-score we will be using is negative 0.33. So then I'm going to go find that, because that's going to give me this area here. Okay? So I'm going to go back. I don't want my positive ones. I want my negative ones, and I'm looking for negative 0.33. Well, it's nice for me. I can just take this guy, and I can erase everything off of it until I come across. And now I'm going to go 0.3. So I got to go. I'm going to take this guy all the way down, because I know I'm taking that column down until I hit this column across. So I got 0.33. There's my intersection. So that's going to be 0.3707. 0.3707. 0.3707. 0.3707. 0.37070, I think, I hope, 0.37070. That's the area underneath the curve. I need to convert that because I wanted a percent. 37.070%. That's my percentage, okay? What I want you guys to do is I want you to do this one quick, and I'm going to hit pause. All right, if you did this, honestly here, we're looking for 16, above 16 inches. So I came up here, I drew my line at 16 inches. We're looking for this area up here. So remember, your z-score is going to give you to the left of the curve. So what I had to do is I had to come down here and take my z-score. I took my data value minus the mean divided by 3. I get 5 over 3. Hey, that converts to 1.6 repeating. But remember, we got to accurately, if you give me 1.66, it's going to be wrong. So we need to look at that third decimal. Hey, that means round that 6 up. So my z-score is 1.67. I come back to my Z chart, and I go to 1.6, 1.67, and I get 0.95054, 95054, no, 95254, 95254, and I get 0.95254. But that right there, that's below the curve, or below the curve. We want it to be above. So we have to take the whole area of 1 minus the area to the left to get our area to the right, convert it to a decimal. 4.76% of trees will be above the diameter of 16 inches. Not a lot of them, okay? Now let's go back to our original problem. Knowing the mean composite ACT score for 2020 was 20.7 with a standard deviation of 5.9, what percent of ACT scores were below a 21? I'm going to hit pause. I want you to go find that. All right, so because we want it below, a lot of times, guys, if you don't have a diagram, it really helps you to just make any old normal curve, slap your mean in the middle, plug your data value to the wherever it's got to be, if it's right or left of the mean, and we want to know where it's below 21. So we're looking to the area to the left of our data value. Well, in order to find that, and the nice thing is our z-score gives to the left. In order to find that, we got to find our z-score. So we need to take our z-score, and we need to take our data value minus our mean divided by standard deviation. And they gave us those two in there. So I take 21 minus 20.7 divided by 5.9, yada, yada, yada. I get 0.0508. Remember, we need to adequately round to 2 decimal places. So I look at the 0. That makes me do what with the 5? Oh, my z-score is going to be 0.05. So then I go to my z table. On the positive side, by the way. So I go 0.05, ooh, 0.050. So 0.05, 0.05, right? Now I go, ooh, I don't go there. I go 0.0, right? I got to take 0.05, and there is my area to the left, 51.994. It's easy to lose decimals in this chart. No? Whoa. Well, then I come to my chart. I'm like, yeah, there's my area to the left. I convert my area into a percent, and it says 51.994 people scored below a 21 on the ACT in 2020, okay? So this says, why is their estimation lower than the rank that's listed on the sheet? So they're coming back here and they're saying, hey, here's my rank, here's my state rank, and here's my US rank, and they're saying the composite score of a 21, this is a random sample off there, is a 56 with US, and the state rank puts it at a 58, but we just calculated that to be a 51.994. Well, that's kind of odd. What's the difference? Why is it there? Why are we lower than what that actually rank is saying on that explanation? Well, there's 2 reasons. It may be that our data is not actually normally distributed. Okay? It might be skewed a little left. And if that's true, I can't use my normal distribution. However, it could be that the ranks do not affect current data, meaning when they copied and pasted this onto your composite score, they might not, these ranks, all this data right here, might not be reflected from the year 2020. Maybe it was from 20, or maybe it was from 2010 or something. And they just got lazy and they didn't redo that. They're like, hey, we don't need to do that and tell people how to read it. We have one example. This tells them how to read it and go from there. So that could be the other example. So from here, we have completed this. Sorry, this video is longer, but now woohoo! Now you can finish that. Do not lose that z-score chart on the front. We will be working with that dirty, rotten scoundrel tomorrow. Hey, guys, thanks for playing math today. We'll talk to you tomorrow.